Today I'm going to be talking about DESI, which has been using NERSC for about 10 years, but some of it builds on work from prior experiments. This will be a fairly casual talk reminiscing about ways in which we've, making our map of the universe and how we do it and how NERSC has enabled that. And also spending a few slides on ways in which we've maybe been using NERSC in what used to be surprising ways that are becoming increasingly common. Because I feel like we're always at the bleeding edge of what users are asking for. So this is a picture of our telescope. Maybe I'll try to use the mouse to help folks online. So that's the Kitt Peak Observatory. That's the Mayall telescope. It's in southern Arizona. That's where we get our data for making the map. And there we go. So I wanted to start out with a sciences art entry for the NERSC 50th anniversary celebration. This shows 0.1% of the 3D map of the universe that DESI is making. So Earth is down here in the corner. I keep coming at the screen instead. Maybe I will. I'll keep pointing at the screen. So Earth is down here in the corner. We're looking out at the universe. There are certain directions that we can't look because our own galaxy is in the way, and we're mainly interested in things outside of our own galaxy. We're also limited how much we can see to the south because we can't see things like directly below the South Pole because our telescope's in the north. But every point on this map represents a galaxy, and each galaxy itself has hundreds of billions of stars in it. And all of this structure that you see of like dense areas and voids and filaments connecting them, that's all real structure in the universe that comes from how gravity is pulling things together, dark energy is pushing stuff apart, and we're making this map and studying the statistical properties of how stuff clumps and moves around and looks. Also, the light that's coming from stuff way out here is about 10 billion light years, or 10 billion years old is when the light left and came to get to us. And so we're also looking back in time at what was the structure of the universe billions of years ago compared to what is the structure of the universe more local to us. And so it's fun. It's gonna be, it's neat. And so to start making that 3D map of the universe, the first thing we had to do was make a 2D map of the universe, which basically you take pictures of the sky, like the background here, and then you fit for each of these little blobs to identify an object of where it is, what its colors are, what its shapes are, how bright is it, stuff like that. But to make the 2D map that we needed to combine data that was better than any one data set in the world. And so we ended up combining data from 4 different telescopes on Earth, 2 different satellites. These were funded by 6 different funding agencies spread across 4 continents that were hosted from 4 different data portals, some of which only allowed you to download postage stamps of the images, 1 HTTP query at a time. So that particular data portal, we kept melting their server and filing help tickets until they helped us get all the data. But we basically brought all the data at NERSC because getting like a little bit of data here, a little bit of data there didn't do us any good when we wanted to simultaneously fit all of this. And so actually getting it at NERSC where we had the computers to go with the data across all of these different continents and funding agencies allowed us to actually make the measurements in the level of detail that we needed. And we were able to find objects that you couldn't see them in any one of these data sets, but when you fit them simultaneously and join them together, you get the extra signal to noise to allow you to find those super extra faint objects. And so this 2D map has 2.8 billion objects in it. More than half of those are not stars in our own galaxy. They're galaxies and quasars far out there. And the different generations of making this map have spanned Edison and Pori, and now we're working on making the next version of this using Perlmutter with even more data that we've obtained in the meantime. And then because all of this in some sense was just precursor work for DESI, we're like, well, let's just make the data public. And so the data are publicly served at this URL, which is running on Spin, hosting the data from NERSC. And as of last Friday, there were 671 papers published using this. That was just our predecessor project for getting ready for DESI for making this. And if you want to have a little bit of fun, you can go to legacysurvey.org/viewer. And it's basically like Google Maps for the sky. And so you can zoom in and out. get a sense of the scale of this data set. It's pretty fun. In terms of, we were invited to give anecdotes. One of the early versions of this was hosted directly from NERSC. It got picked up on Reddit, and we got the Reddit hug of death. And it came in and completely overwhelmed the servers. And so now the public-facing version of this we actually host from Amazon, so we can take Amazon down instead. But we do run a version of this at NERSC for ourselves that has faster access to the data and can see that our work in progress before we make it public. But it's just, I love this file. I love the data sets. So then switching for how we go from that 2D map of where things are on the sky. Go back to here. The next trick is to figure out the third dimension of how far away are these objects. And the way we do that is we get spectra of the different objects, where I will now go to another entry in the Sciences Art competition, where this is actually turned on its side just so that it fits a little better on the slide. But what we're looking at here is vertically is the wavelength of light of one of these objects on the sky, where bluer light is over here and redder light is over here. And a galaxy has these various bumps and wiggles of certain wavelengths give more light than other wavelengths. And then these are coads of DESI data for things that are from a certain distance away from us. And this is measured in basically time the light spent to get to us. And the most distant objects up here in white are around 10 billion years the light left that long ago. It has been traveling through the universe just in time for us to, there's a joke from Saul Perlmutter about it. We built the telescope just in time to catch the light before it arrived. But you can see that these bumps and wiggles evolve with time, and they also have this shift in wavelength, that something that's very distant is at one wavelength, and if it's closer in, it's at another wavelength. And so we measure these spectra and look at these bumps and wiggles to see how much is it shifted to be able to locate each object for what its third dimension is, for how far away it is. And so to do that, we start with our 2D map of the universe. We can't observe all 2.8 billion objects in that map. So we sub-select objects that we think are representative of what we want to measure at different locations in the universe. And we pick out mostly little tiny things that are very far away. Things like this are like way too close, that we're not interested in those galaxies. They're just in the way. So we pick out each one of those and we put a fiber optic cable at the location of that galaxy. And then the fiber optic cables get routed down to the other end of the cable bundle, where we line them all up in a row. And the light coming out of that end of the fiber optic cable, we basically put it through a fancy prism, and it spreads the light out. So you get different wavelengths of light at different locations. This is what our raw data look like. But most of what you're seeing here, so we have wavelength in this direction, different fibers in this direction. All of these lines that look the same for everybody, this is basically the brightness of the sky. So the nighttime sky is bright compared to the things we're looking at. All of those weird squiggly things are cosmic rays coming in from outer space, hitting our detector, blasting through it. The actual signal we're looking for, you can't see by eye. It's buried in the noise of this image. And that's where we need the NERSC supercomputers for analyzing this in extreme detail, getting the absolute last bit of statistical information out of these data, so that buried down there in the noise, we're getting those little bumps and wiggles from those galaxies and measuring where they are in redshift. And so in practice, the way DESI does this is we have a focal plane that has, we're looking at this focal plane, there's 5,000 little robots. Here's a zoom in on them. Each one of these robots is holding a fiber optic cable. That little tiny dot there, it's about the size of a human hair, is a fiber optic cable. And then these are little robotic arms that can move around. And so when the telescope points at some location on the sky, those robots then move around to get that fiber optic cable on the location of a galaxy. And then we start exposing. This is an amazing mechanical feat, because this telescope is several stories high, this giant object. These things are about the size of a human hair, and just the Earth rotating, it goes 15 diameters of that size in 1 second. And so we're constantly having to move the telescope and move these things just to keep up with the fact that the Earth is rotating out from under us while we expose for 15 minutes. But our accuracy of being able to place these things and hold them on location, so this is about 100 microns across, 107 microns. We can get these to 5 microns and hold them there. So, a small fraction of the size of that tiny thing on this gigantic telescope. But that's what we need to be capturing those photons of light that have been coming across the universe to us for 10 billion years, so that we can then read out the data and send it to NERSC. So our daily operations, or maybe more aptly our nightly operations, are we have our telescope at Kitt Peak in Tucson. We have semi-real-time data transfer, copying the data to NERSC, where in the real-time queue, as soon as it arrives, we start processing it. Because we're making quality assurance, QA, data that get fed back to the observers for if anything goes wrong with the instrument, they know immediately that there's something wrong and they can react and fix it. And then we also have a more complete version that sort of takes all night to process the data, but we wake up in the morning and the full version of the pipeline has also run. And then we use that to update the survey plan based on what did we observe last night, what do we still need to observe? That data was bad, we need more signal to noise, go back and observe that, or we're done with that, move on. And so there's this feedback loop to the telescope going on a daily basis. At the same time, if that was all we were doing, we would probably just buy 10 big computers and call it done. The part that really drives us to wanting to use NERSC is this other path of every year or two, we reprocess all of the data we've taken to date using our latest algorithms, latest calibration, and we don't want to have to wait around years worth of processing to do that. And so this is where we use the big iron to process that. And then we give that data to our hundreds of collaborators worldwide who are all logging into NERSC to do their analyses, some of which also need the NERSC big iron to be doing simulations and analyses and studying those statistical properties. And that runs into the cosmology papers. And basically you do this process, you're getting 5,000 spectra at a time, about every 15 minutes through the night. We observe every night of the year that it isn't cloudy, and even when it is cloudy, somebody's waiting there in case the cloud's clear. And then we do this every night for 5 years, and that adds up to tens of millions of spectra. So we're currently in our 4th year, we're coming up on our 4th anniversary of that, so we're 3 and some years in. But we also have extensions to DESI and upgrade projects, et cetera, that'll take us another 15 years or so. So we're not going away. But this is our operations flow. So putting context of where DESI is in NERSC, this is back from 2020 because I stole a screenshot from Debbie, I think it was. But it's looking at that time, how much data do different projects have at NERSC versus what is our allocation in millions of hours back in Edison or Corey days, whatever that was. And we're up in the top 5 users of data across compute for doing this. And then curiously, we have hundreds of users at NERSC, so we're about 10% of the users. And so that's one of the things I really appreciate about being at NERSC is that there's a help desk and account management support doing that. And rather than me having to manage hundreds of users, it's great to have a site that supports us and supports those hundreds of users, most of which I don't even know. And related to that, DESI does use the full NERSC ecosystem. We often emphasize the compute aspects, both the real-time queue for the daily processing, the big iron for these quarterly or yearly reprocessing and science analyses. But we also use all the different forms of I/O systems. We use the data transfer nodes and Globus, and we have our own spin container running a website portal for us. We use various workflow things. A lot of the analysis, especially with the more junior members, is run through Jupyter, but we also have analyses that are running up to the regular queue using hundreds of nodes, massively parallel jobs. And having all of this in a one-stop shop is a uniquely great thing at NERSC. It's not just that there's big computers and big disks, but it's like all this other stuff that wraps around it is what makes NERSC uniquely valuable for us. And we really appreciate Daniel Margala is our liaison for the super facility. And I already mentioned the user services for all the account management and helping manage those. So this is why we're at NERSC. Now I want to go into some of the ways in which we're somewhat unusual users of NERSC, at least historically. So something that used to be an unusual mix becoming more common is, first of all, DESI was designed for HPC from the start, while at the same time we were written in Python from the start. And this has been a very effective combination for DESI. So I want to spend a few slides just going into what this means for us, how it's worked out, where some of the challenges have been. So first of all, designed for HPC from the start, we did have the advantage of we decided not to port any legacy code from prior experiments. They were getting a little long in the tooth. We said we want to take the ideas and the algorithms and some of the philosophy from that, but we're going to write it all from scratch. This gave us a fresh start to implement new ideas. It helped us modernize some code practices. This was part of porting it into Python. And so when we did that, we said we want to design for HPC from the start. And what we meant by that was we did consider how parallelism would be folded into it from the start. And we accepted the reality of what things like the memory per core was going to be. Some legacy codes are extremely memory hungry, and then they come to an HPC center and they're like, or they have absolutely no parallelism at all, and then it's like trying to shove it into, things like the serial queue help a lot, but we were aware of those things when we started writing it. But things it did not mean was, it didn't always mean using classic HPC design patterns. It certainly didn't mean using a classic HPC language. And it also didn't mean accepting NERSC as is. We've tried to have a very constructive collaboration with NERSC as a positively squeaky wheel, where we're saying, this part isn't working for us. How can we do better? And sometimes the answer is NERSC does better, and sometimes the answer is they help us be better. And so I think there's been a good collaboration where both sides have been flexing a little bit to find the solution and not just shoehorning one thing into another. So that's been good. I can't quite take credit that all of these things exist because of NERSC, because of DESI, but we were early adopters of things like spin and collaboration accounts and various workflow things and the read-only CFS mount. These have been driven by users like DESI that keep doing things like melting the CFS by our IO patterns and the optimization of that. And we've had ongoing advocacy for robustness of the system, and can you keep things up when you're doing maintenances? So this is part of that collaboration. I saw something pop by from Zoom. Was that a question? There's a 10. So going into one example of a non-traditional HPC usage. So I mentioned our telescope is taking exposures every 15 minutes or so. And logically, most steps of the pipeline can be processing those completely independent. So we're looking at that patch of the sky, that patch of the sky. They don't have anything to do with each other. We just process them. Our initial design was, we will be HPC. We will bundle these together into massively parallel jobs. We'll have this incredible throughput. Computationally, that was most efficient. It was the most HPC-like. The problem was that a failure of any one piece basically took down everything else with it, even though it was completely unrelated. And sometimes those problems were admittedly ours, some algorithm that quarter case or a data quality issue or something, or sometimes they were NERSC's problem, like a bad node or some IO hiccup, and like one rank would get hung writing a file, and then we had hundreds of other nodes sitting around waiting for that one to catch up. So we ended up saying, okay, that's not working great for us. We switch now into a model of, we have a very large number of independent small jobs processing all of these different pieces of sky, and then stuff at the end puts them together. These are typically single node jobs that run for around 20 minutes each. This makes it much more robust to individual failures, because the failure just takes down the one thing that it's actually impacting, not everybody else. And it's also easiest to recover, because if it is a problem that was on NERSC's side, we just resubmit exactly the same job and it just recovers. Or if it's a problem on our side, we have this one tiny thing that we have to debug, fix, and submit just that one thing. It's not caught up in the rest of the massively parallel job. But the problem is, it is less efficient. And for our latest run, we are getting around 50,000 jobs, which right now the queue limits are like 5,000 jobs. And so we're now hitting this like more hand-holding of just like, how do you submit those jobs given those limits? And as things become faster and the machine's more stable, it becomes more attractive to bundle things. And even going from Cori to Perlmutter things that previously were split apart got bundled more for Perlmutter, and now we're looking for our next run. We'll probably bundle it. In the interest of time, I'm going to skip that one and go on to the written in Python from the start. Another anecdote, 20 years ago, shortly after I had started working at NERSC, we were using Python to coordinate job submission and do some like parsing of log files and stuff like that. And I needed some additional library. I don't remember what it was, but it was some third-party library. And this was before like Conda days or Docker. Like we couldn't install it ourselves. So I submitted a help ticket and said, can you install this library? And the answer was no. And the cited reason was Python is not an HPC language. We don't support it. Deal. And so, you know, part of that constructively squeaky wheel, we like kept using Python anyway. And over the years, you know, fast forward, Python now has first-class support at NERSC. It's great. More users are logging in via Jupyter, which is dominantly Python, than SSH. And third-party libraries have caught up to make Python a very effective HPC-light language. Where for DESI, what our Python toolkit is, first of all, MPI for Pi for parallelism, so we can scale up. We use NumPy and SciPy to leverage compiled code written by other people, not us, so we don't have to write compiled code. And so we do like a lot of linear algebra. So those things are just, you know, they're in LAPACK, other people are wrapped in, it's great. We use the Numba library for just-in-time compilation of code, so we can write it in Python and it gets compiled on the fly, go faster. And then we use CuPy for GPU, while that also, because it's basically a NumPy syntactic replacement, it makes it easy to have a CPU path and a GPU path with minimal like code separation. It's the same code, it just at the very beginning says, should I be using CuPy or NumPy? It's exactly that simple, but it's flavor-wise, that way we can maintain a CPU-only path for running else. So coming full circle on HPC plus Python, one of our remaining codes is still CPU only. It's C++, and it's taking about 15% of our production time. And as we were discussing, how are we going to port this to GPUs? The current plan that was thought the easiest is to port it to Python first, and then port the Python part to use CuPy to port it to GPUs. And so, you know, more classic HPC people in the room or on Zoom might be feeling like the exploding head emoji of like, this is a travesty that we are taking compiled code into Python to run on HPC. But for other users, it's like a breath of fresh air that we can be using Python very effectively, very efficiently for humans for sort of the fastest time to solution, even if it's not the absolute most efficient on the computers. We found it to be the fastest time to solution for the humans for getting our science. I do have to put in a plug for the NESAP program. This has been fantastic for us, the NERSC Science Acceleration Program. Round one with Lori Steffi and Roland Thomas was our like manager at that point, made our code 10 times faster on Corey Haswell compared to what it was running on Edison prior to that. We didn't get nearly that much speed up on the KNL CPUs, but it made it fast enough that KNL actually became viable for us to use, and we didn't have to wait a gazillion hours. And so that's, the NESAP program was what allowed us to use the Corey KNL. Then NESAP round two, porting to Perlmutter GPUs with Daniel Margalla. We got an additional 17.6 faster, so you now multiply those, you know, 176 times faster than we were running on Edison. It's almost embarrassing how much faster it is now. That was a real game changer for just how quickly we could push these big data sets through. And we're currently in round three with Soham, and now Daniel Margalla is more of the manager role, he's, you know, graduating. This is ongoing, porting other portions of more of our science side of the code rather than our data processing. But it's really been a game-changing partnership between NERSC and DESI. So thank you for the free postdocs. It's been great. So talking about our data releases in the last few minutes here. So every few years, I mentioned we do these reprocessings, and then these are the things that we write our key cosmology papers on and then release to the public. And so the processing for a year one data set, it has, you know, lots of jobs, lots of files, lots of terabytes, and it takes about 2.5 weeks to process at NERSC. In our year three data set, it was an even bigger data set, depending on the metric, you know, 2 to 3 times larger. But because we were using Perlmutter and we just had lots of nodes available, you just use more nodes, and it actually took us less time in wall clock to process that new data. This is in comparison to prior generation experiments. A tiny fraction of the DESI data used to spend months doing their processing on custom clusters that they own. And so using mainly the year one data set, because this came out just a couple weeks ago, we have over 250 papers from the DESI science collaboration. There's an additional somewhere around 100 papers using an even earlier version of these data. I didn't do a complete, there's 187 of those papers, but I didn't count which ones were coming from DESI and which were coming from others. But and then there's additionally hundreds of citations to these research, and publication-wise, we're just getting started. And so I expect within a year, we might, if you count the 2D map papers plus the 3D map papers, we might be getting up towards the 1,000 paper mark for the work that has been able to run here at NERSC. So I just want to end with thanks to NERSC for a very fruitful partnership over the last 10 years as we've been developing DESI and then running DESI. The NESAP program, the storage group, we are a pain in their side, but they have been working with us to get things working great. Especially Lisa, who's our interface to the storage group. User services, the super facility program has been great. Thanks also to management. I know we are probably a pain in their side too. And to the DESI users who have been using NERSC and adapting to life on a supercomputer to make this beautiful map. Thank you.
Thanks, Stephen. Well, I don't know if we get kicked out of this room, but we have a few minutes, and if anybody has any questions, please type them in. There is one already. So going back to the telescope, how do you calibrate the robots so you know they're pointing at the right place?
So we actually, as part of the system, we have a camera that looks back at the focal plane, and we have a way to light the fibers from the back. And so we can make the tips of all of the fibers glow, and we take a picture of that. And then we analyze that picture to see where are the fibers compared to where they should be. And then we do an additional correction. So the first time we tell them to move somewhere, they're accurate to about 30 microns. And then we take that picture, analyze it, and say, okay, move a little bit that way, move a little bit that way. And that gets us, that second move gets us to the 5 microns.
Has anybody programmed any cool animations for the incident?
There are, but I don't have them in my slide deck.
And then the follow-up to that was also, do you do any compensation for atmospheric effects?
Yes. So there's actually, as part of the lens system flowing into this, there's a set of counter-rotating prisms that basically the atmosphere acts as its own prism, spreading out the red light differently than the blue light. And then depending on where we're looking on the sky, we rotate prisms to counteract that, to bring the red and blue light back together so we can get it all down the same fiber, the red
light. Do you expect, or how do you expect the way in which you're using the system to change over the next couple of years?
I can't wait till NERSC 11 is a quantum computer and then we can rewrite our no. So in some sense, that is one of the curses of working in an HPC system, that we're using a small fraction of Perlmutter. We like Perlmutter. We'd be happy with continuing to use Perlmutter for the next 10 years, but it keeps getting changed out from under us. So even if NERSC 10 is better, it is kind of this disruption that you have to adapt again. Over the next 10 years-ish, our data volume will continue to grow, but there won't be this phase transition of huge amounts more data. Another project coming about 10 years from now they'll be replacing these 5,000 positioners with 25,000 positioners and bigger telescopes, and data will be coming in a lot faster, and we'll need bigger computers then. But for the most part, it's if we just keep using Perlmutter like we use Perlmutter or NERSC 10 just like we do, that would be great. I think Shane has his hand up.
Yeah, I was just curious. It was on this one too. Are you able to put to place a fiber? Does every fiber get lit with something interesting, or is it a subset of them do, and then some are just looking at?
Yeah, so
space?
each fiber can only see kind of the local area.
Yeah.
And we have a high enough density of targets that most fibers can get to some object of interest.
Okay.
And then the other objects of interest that we didn't get to, we come back and look at the same patch of sky again. Sometimes, particularly blank spot of sky, a fiber may not have anything to look at.
Yeah.
But part of our calibration is we also have to be looking at purposely blank sky locations so we can subtract off what that blank sky looks like. And so we use those fibers for calibration data to remove it anyway. So they're not wasted.
I have a question about batch data processing. So you said you have tens of millions of small jobs.
Mhm.
Do you have a threshold for the failure that you don't try to resubmit? Like you don't pick a penny, right? Because it's
Yeah.
do you have a threshold like this?
Um,
Not worth to spend time of your employee.
So if we believe it is a recoverable problem just by resubmitting the job, no bit is left behind, we resubmit the job. There are corner cases of, sometimes it was a lightly cloudy night and we were just barely getting enough signal to noise and there's a problem. We might throw that data away to say it's not worth chasing bad data. But if we believe the data is good and it's just the computers are bad, we chase that absolutely down to get back.
All right, so more questions online. Catch up with some of those. For your CPU and GPU issue, have you explored using something like Julia as a single language approach?
Yeah, so
there.
when Julia came out, I was super excited about it, and I thought it was totally going to eat Python's lunch. And I'm surprised that 10-ish years later, it's Python is the thing we're still using and not Julia. But Julia is amazing, but there also hasn't been this threshold effect that it's worth rewriting everything to Julia and bringing that in as a dependency. That project I mentioned 10 years in the future where everything's going to be much bigger, we might take that opportunity to rewrite everything again. And if we're rewriting everything from scratch again, I would seriously consider Julia at that point.
So on the DESI viewer with DR10, I'm not sure what DR10 is, but anyway,
Data release 10.
data release 10, I see some purple galaxies.
Yeah, so some of that is the colors you see on the viewer come from, we take images in different telescope filters, but sometimes we didn't get the reddest filters on some patch of sky. And so we just don't have the red data. And so the processing as it renders it into the false color image for the viewer, it ends up showing purple. In the actual data we're using for science, we know that it's missing red data, not that the red is 0, therefore it's purple.
I guess this room is reserved, so we need to vacate.
Okay.
So thank you again.
Well,
And
thank you.
then Nick, you can take your question offline. His question about HPSS capacity.
We treat it as infinite and we thank you for it.
Thank you again.
That's the phrase.